Okay, so we're very pleased to have Ari Shnidman, who will tell us about Hilbert's 10th problem over rings of integers.
Here, patient. Yeah, so this is all joint work with Levent Alpöge, Manjul Bhargava, and Wei Ho. So let me remind you what Hilbert's 10th problem is. So slightly informal version of it. So Hilbert's 10th, this was asked in 1900. So informally, is there an algorithm that determines, so to determine solubility of polynomial equations over, that's the question. So meaning, is there some code we can write up for a Turing machine such that given any polynomial with coefficients in Z, the Turing machine will tell us yes or no whether there are solutions to the equation polynomial equals 0, with the solutions being in Z. And that was the question. And this was this board. So this is in 1900, and then theorem due to Matyasevich, he finished off the proof. This is in 1970, but people refer usually to this theorem as being due to Matyasevich and Davis, Putnam, Robinson. So he was building off of their work as well from 61, and the theorem is no. And so there is no algorithm to do this, and so I've stated their theorem in a very negative way. But you should really think of their theorem actually as being something positive, and it's quite an interesting fact, at least in my naive mind. I'm not a logician or a set theorist, but what they're really proving is that any subset of the integers that you could create by encoding some program, putting it into a Turing machine, and letting the program run indefinitely forever and seeing what the Turing machine prints out, any such subset is what we would call Diophantine. It is the zero set of some polynomial, possibly in many variables, where you look at the zero set in the first variable and you allow all the other variables to range. So to me, that's like some kind of an amazing statement about Diophantine subsets, that they encode anything that a Turing machine could write down. And a consequence of that ultimately is that, yeah, there is no algorithm to determine solubility of polynomial equations. So this is the theorem from 1970. And of course, the natural follow-up is, well, what about if we replace Z with Q? Then this is an open question, presumably a very hard open question. Another natural follow-up, especially considering the fact that this is a question that is about computation, is what about more general rings, more general computable rings in which we can do computation. So rings that have like a finite multiplication table over Z. So the natural generalization would be, this is the topic of the talk, is what about over other finite rings, such as finite over Z, okay, ring of integers of a number field. Okay, so that's the question. Same question, but where we allow the polynomials to have coefficients in OK, and the solutions are allowed to be in OK. So there's a lot of work on this question, and maybe I should say from the onset, you might ask, well, why don't you just try the same proof, but do it over OK? And the very first thing you'll want to do if you try that approach is you'll want to see, how can I define Z as a Diophantine subset of OK? But already that's the whole problem. That's enough. And so this is really what the question is. Let me just state it as a remark, and I'm not going to define carefully the notion Diophantine. I'll say it out loud, but it's enough to show that Z is Diophantine in OK. It means that they're, roughly speaking, I don't want to write down a careful definition, but it means that there's some polynomial with coefficients in OK such that Z is the zero set, is the solution set in the first variable of that polynomial. It's exactly the the elements of OK that you can stick them into the first variable and then fill out the rest of the variables and to get 0. So that would be saying that Z is Diophantine and OK. And very easy, if you think about it for a little bit, you'll see that if Z is Diophantine and an OK, we combine that with the negative result over Z, you'll see that, yeah, you can't have an algorithm over OK either. So this is really the question, is Z Diophantine and OK? It's enough to show that it is Diophantine and OK. And so again, we're gonna try to prove this, which again is a positive statement. It's not a negative statement. Okay, and so yeah, there's a lot of work on this. Maybe the first big class of number fields for which it was known is a theorem of Denef in the 80s. So true if K is totally real. And already in Denef, maybe not in this paper, but soon afterwards, Denef realized that to try to show that he was Diophantine and OK, you can exploit. It's kind of analogous to what happened here. Maciejewicz exploits the Pell equation and the existence of an infinite rank 1 group inside the solutions to the Pell equation. And Denef realizes that you can, and many other people, that you can use abelian varieties and their rational points of positive rank to try to show that Z is Diophantine and OK.
Sorry, I could ask this question for any ring, as you said, right? Is there some kind of reasonable guess I could make as to its answer? Suppose I don't care about proving things. Well, what do we think is true?
Over any ring or over which ring?
I don't know. Is there a sensible thing you could?
Yeah, so I think, so you said finitely generated. So I think
finitely generated.
I think this implies that finitely generated case also has a negative solution. Except, of course,
for any finitely generated ring.
Unless it's finite. If the ring is finite, then there's certainly an algorithm. But yeah, any finitely generated infinite ring.
Okay. Okay.
It's known. And then and then beyond that, it's like I wouldn't know how to. Yeah. Okay.
Is there any expectation for Q?
I think the expectation is that no, there shouldn't be, but I don't know. And Mazur has some interesting conjectures about the topology of the real points of algebraic varieties that would imply, and I think, a negative answer, but I don't remember. So look on Wikipedia. Yeah.
In the definition of Diophantine, does it allow Boolean combination of polynomial equals 0?
I don't think so. But I'm not being precise. In a month from now, I'm going to give a members colloquium where I'll actually learn a little bit more about these definitions. And because what I'm about to say is that it's been known for many years now that this question reduces to a question about Mordell-Weil groups of abelian varieties. And that's really what Chuck will be about. And I'm not yet expert enough to know all the different possibilities for the definition. So Denef realized that you can use abelian varieties to attack this question. And so, for example, I'll write down or maybe I'll write it down. I'll do it here. So, for example, in 2010, Mazur and Rubin showed that it's true for all K number fields, assuming. So it was a conditional proof. So you had a condition on the finiteness of the Tate-Shafarevich group. Assuming, let me just give something much stronger than what they really need, but just to make it shorter, just finiteness of Tate-Shafarevich group of any abelian variety over any number field, let's just say. So they give a conditional proof. And so what is the actual input from about abelian varieties that one can use? So this is a theorem of Shlapentokh. So Sasha Shlapentokh has worked a lot on this problem with many results. Here's a criterion. If for all extensions K over F of number fields, the following thing holds. If for all K over F there exists an abelian variety A over F such that A has positive rank and its rank doesn't change when you base change. So if both of those two things are true, then Let's see, how do I want to say this? Let me just say it this way, then Hilbert 10 has a negative answer. I mean, the right thing to say here is that then OF is Diophantine and OK. But let me just say it this way, then H10 has a negative answer for all OK. So, which is really a consequence of the precise thing that it's proving. Okay, I won't go into this. Maybe in a month from now, I'll say a little bit more about how it's kind of like this Pell equation type argument. You use the fact that you have infinitely many rational points to write down a Diophantine definition of OF inside of OK. What I will use now is a further remark or observation of Shlapentokh that in fact, you don't need anything as strong as this, any extension. In fact, it's enough to just look at quadratic extensions. That gives you everything. And that's, maybe I'll just draw the picture. Just, this is a simple formula. Just explain how, so, let's grant that it's true for all quadratic extensions. And I'll explain how you deduce it in general. The way, I'll just do it by drawing a picture. So the way you do this in general is you can imagine that it's enough to, let's say we're trying to show that that Z has a Diophantine definition inside of OK. Then you can imagine that we can assume K is Galois by replacing K with its Galois closure. And therefore, well, if it's totally real, Denef has already proven what we wanted. So we get to assume it's totally complex. And therefore, we have a bunch of complex conjugations. And let's just say for the sake of this drawing that there are 3 of them. And we can intersect them. And they intersect in a totally real field. So Denef's result applies to this extension. We're granting these extensions because they're all quadratic. They come from complex conjugations. And you can check, it's a formal thing that if you know OFI is Diophantine in OK, then OL, the intersection of all of them, it's Diophantine in OK as well. And then by transitivity of this notion of Diophantine, you deduce the whole result. So by this argument, which I didn't write out in full, but sketched, you can actually reduce to just the question about quadratic extensions. So that argument is also due to Shlapentokh. Okay, so that's what we prove. So this is, like I said, joint work with Levent, Manjul, and Wei. So that K over F be a quadratic extension. Number fields. Then there exists an abelian variety A over F such that, well, the same condition is with it. It has positive rank, and when you base change to the quadratic extension, the rank stays the same. Okay, and so the corollary, if you've been following the thread, is Hilbert's 10th problem has a negative solution. Over OK for all number fields. Okay.
So we need only one quadratic extension.
Yes, for a given, that's true, is that, in fact, if you fix F, you only need to prove this for the Galois closure, if it happens to be quadratic, that's true. Somehow that doesn't seem to help one way or the other, use that information, or not to us, it hasn't. Yeah. Okay, so any questions on the statement? Let me make an important remark now. So this is an unconditional proof. Maser and Rubin gave a conditional proof, but 2 months ago on the archive, Koymans and Pagano also give also prove this corollary. So they also show Hilbert tensor have a negative solution over OK for all K. And it's similarly, we'll use abelian varieties. They don't quite prove this theorem, but they prove enough of cases of this theorem to make the conclusion about Hilbert's tenth. And which abelian varieties do they use? They use y squared, so elliptic curves with full two torsion. So the Legendre family of elliptic curves. So they show that given K over F, at least many types of K over F, you can find elliptic curves of this form that satisfy the conclusion. We're going to use, and they use two Selmer groups, so two descent. We're going to use, in general, higher dimensional abelian varieties and a different kind of descent, odd degree descent. Okay. So this is from 2 months ago. And the proof is not too long, so I'm gonna try to basically give the proof of, it's a construction and a proof. But maybe I'll just say quickly, like, why is this a hard question to begin with? Like, what's the meat here? Why does it take so long, 40 years or whatever it is to prove this kind of thing? The point is that you're trying to do two things at once. You're trying to produce rational points on abelian varieties, but then you're also trying to constrain them. And both of these things individually, we know very well how to do. I mean, producing rational points is very easy. You know, y squared equals f of x, a hyperelliptic curve, just put in values into f and then quadratic twist appropriately. There you have almost always an infinite order rational point. Similarly, you know, bounding the ranks of abelian varieties, we have about 100 years of Selmer group technology and knowledge to do that. We know very well how to bound ranks of abelian varieties, but somehow when you try to do both at the same time, it gets harder. And so I don't want to write this on the board, but here are two related or questions of a similar flavor. One of them open. So given a number field, is there an elliptic curve of rank 1 over that number field? Open question as far as I know, and it's the same flavor. You're asking for rational points, but not too many. And we don't know how to answer that question as of right now. Another open question, when I gave this talk 3 weeks ago at Harvard, I said a second open question, which was show that there are infinitely many elliptic curves over Q of rank 2, which 3 weeks ago was an open question. But 2 weeks ago on the archive, David Zywina gave a proof. And the proof is kind of has similar ideas even to the proofs of our result and the Kleiman-Pagano result. Vague ideas, not the same proof or anything, but so you'll see like how this is done in the proof. Okay, any questions? Okay, so let's start the proof, and we're going to start with a reduction step, and this reduction step is going to determine the dimension of the abelian variety. It will determine which abelian varieties are we even going to look at. So say we have K over F quadratic, and let's take an odd prime L. So let L be an odd prime, not dividing the discriminant of K, let's say. Then in particular, the L cyclotomic field is definitely not in K, and it's linearly disjoint from K. And so, right, and so it's enough in this case, so it's enough to prove the claim. We're trying to show that there's exists an abelian variety over F, blah, blah, blah. So there's enough to prove the claim for the quadratic extension K adjoin zeta over F adjoin zeta, where zeta is primitive Lth root of unity. So really, basically, the only thing I'm really just asking is that an Lth root of unity is not in K. Or in fact, the stronger thing is basically that this quadratic extension is not the one that gives me an Lth root of unity. But for technical reasons in the proof, I mean, which I will not actually talk about for the rest of this talk. It's also useful to know that here, this is an unramified extension at L. At all primes above L, this is unramified. So what I'm getting from this, oh, I didn't say, it's enough to prove the claim for this via Wei restriction. So the point is that this is still a quadratic extension. And so if I can produce an abelian variety over this guy with positive rank and whose base change is the same rank, then I can very restrict that abelian variety down to F, and then it will have the right properties with respect to this extension. So by very restriction, I get to assume that the Lth root of unity is in my ground field, and also this technical thing about the quadratic extension being unramified at all primes above L, which you will not hear about for the rest of the talk. I actually don't know how important that condition really is, but we use it in our proof. Okay, so we choose such a prime L, and we're gonna consider in our proof the hyperelliptic curve y squared equals x to the L plus 1 and all of its twists. Okay, and then from now on, I assume the Lth root of unity, primitive Lth root of unity is in my ground field. Okay, so what do I mean by its twists? Well, for any n in F, I can consider the curve Cn, y squared equals x to the L plus n. And this is a genus G. Well, G is L minus 1/2 curve. Okay, hyperelliptic curve. And I'll consider its Jacobian. So the Jacobian is a G-dimensional L minus 1/2 dimensional abelian variety. These will be the abelian varieties that will show up in our construction. And what's nice about these is this is hyperelliptic curve, so it has an involution, and it also has an automorphism of order L. And we're going to use both. So you have UL acting on Cn, and so you get an embedding of the cyclotonic ring into the endomorphism ring of the Jacobian also. Okay, so yeah, like I said, the crucial thing, we're going to use the fact that we have two kind of independent automorphisms on the curve. And let's see, do I need this lemma? Maybe I'll just make this observation. It'll be a little bit implicit in a lot of what follows. It's that if I have a scalar in my ground field, then I can multiply n by lambda to the 2L, and this is the same curve up to isomorphism. So you can check this. And we can use this to give us different kinds of twists. So we have quadratic twists. If you have a quadratic field, let's say square root q for some q, then you have the k quadratic twist, which normally you would write it as, I'll call it CNK, so you write it like this. But it's easy to see this is isomorphic to C and Q to the L. And then similarly, we have the quadratic twist of the Jacobian, which of course is going to be JN Q to the L. So this is one type of twisting that we can do, and obviously this will be relevant to us eventually with our quadratic field. But there's also mu-L twisting, so you also have mu-L twists. Namely, I can look at curves of the form CNR squared and JNR squared for any parameter R. And these are mu-L twists. This is isomorphic to Cn over a cyclic Z mod LZ extension. Just from this, you see it. And so sometimes I'll think of this as kind of living in F cross mod F cross to the L. Okay. And maybe I'll, so for event, so far I haven't kind of started the proof over this field. I'm just talking about the curves. Eventually, we're going to need to choose a very particular abelian variety with this type of condition. And the main point will be at the end of the proof that, so this very well-known fact about quadratic twisting, that the rank of Jn, let's say, over K is equal to the rank of Jn over F plus the rank of Jn K over F. The rank of the base change is the sum of the rank of the original thing and the quadratic twist. Okay, and so then the strategy is you find something of positive rank such that its quadratic twist has rank 0. And then you get what you want. That's the strategy. Okay, in fact, I mean, this is also the rank of Jn k over k. And so in fact, in the proof that I'm about to give, we're kind of going to do the opposite. We're going to find something of rank 0 whose quadratic twist has positive rank, but it's equivalent to what I just said. Okay, so that's going to be the strategy. And to find some, we'll start with the rank 0 guy. We're going to find a Jn of rank 0. And we're going to do that using descent, Selmer groups, and we're going to use very special Selmer groups called, well, we'll call them phi Selmer groups. So let me introduce all that. Okay. So phi is going to be the element 1 minus zeta. And I'm going to always just view the cyclotomic ring inside of the endomorphism ring of my Jacobian. And so far, I haven't chosen n, really. I'm just still just general stuff, but I'm going to view this as an endomorphism. So I think of phi as being a map from Jn to itself, and it has degree L. The norm of 1 minus zeta in the cyclotomic field is L, and Jn has Cm by z adjoins zeta. If you think about the genus, the dimension, and so the degree is just the norm. And so this is an endomorphism, a self-isogeny of degree L. And we're going to do descent. We're going to use Selmer groups for this isogeny. Okay, let me just be a little bit careful because I'll start talking about the curve being points on the curve as being on the Jacobian. So let's embed Cn and Jn in the natural way by sending p to p minus infinity. Infinity is the point at infinity on this hyperelliptic curve. You have a rational point. Okay, so I always think of Cn inside of Jn. Once I do that, we're going to do descent via phi. We're going to need to understand the kernel of phi as a Galois module, and it's very easy. Jn phi, this is the kernel. As a Galois module, it's generated by, well, it's just a one-dimensional FL vector space. With a Galois action, it's generated by the point 0 root n. This is obvious. This is fixed by zeta, so, and it's not 0 in the Jacobian, so it's a generator. And the Galois action, you can see, is by at most quadratic character. N could be a square, then the Galois action is trivial, but if it's not a square, then there's a quadratic character acting. So very, very simple Galois module. And we're gonna do descent in the usual way. So let me, and this is the simplest possible descent that you could ever do. So I'll just write it all out. So let's make some notation. T will be my Galois cohomology, my ambient space. If I have a prime P, suppose I have a prime ideal P, then I have a local Galois cohomology. So FP here is the completion. F is totally complex. I don't care about the Archimedean primes, so all primes will be prime ideals. And then I need to define local conditions to define the Selmer group inside of TP. So we'll let WP be the image of the Kerman map. So the map from local points to TP coming from the usual short exact sequence in Galois cohomology. Okay, so WP is the image of this, and what is the Selmer group? I guess I could define it here. So the Selmer group then, the phi Selmer group, Jn, this is the kernel of the natural product of restriction maps. So this is, I guess, the quick way to define the subgroup. Okay. And this Selmer group, it behaves exactly like, a 2-Selmer group on an elliptic curve or an n-Selmer group in general on an elliptic curve. If you've seen that, and so you have the usual exact sequence involving the Tate-Schaffer-Average group. We don't need the full exact sequence, but all we need is the inclusion on the left. So just from the definitions, you check that this group lives inside of the Selmer group. And it follows that the rank by Mordell-Weil, this is a finitely generated abelian group. It's actually better than that. It's a finitely generated Z-adjoint zeta module. And so the rank as a Z-adjoint zeta module of Jn of F less than or equal to the dimension of the FL vector space self-E. And so the only thing I want from this is just that if the Selmer group is 0, then rank is 0. Okay. So we're going to show not just that we're going to find an n such that Jn has rank 0, and even stronger than saying that Jn has rank 0, it has Selmer rank 0. Yeah, the Selmer group is trivial. And the key player in what follows is going to be this notion that Mazur and Rubin. So we're going to use the methods of Mazur and Rubin in our proof, and they have this notion they call silent primes. And this is kind of the key point in this key kind of technical thing in this argument, is that there are lots of silent primes hanging around. And so here's a lemma. Suppose P is a prime that doesn't divide L, and suppose it's inert or ramified, let me just say inert, in this extension. Okay, then TP is 0. So the local cohomology group just vanishes. This is incredibly useful. It just tells you that, at least if n is not a square. If n is a square, then this is not helpful at all. But if n is not a square, then roughly half of all the primes don't impose local conditions in the Selmer group. Incredibly useful. Why do I want to prove this? The proof is, so first, Jn phi is self-dual as a Galois module. My ground field contains the mu L, the alpha roots of unity, and this is a quadratic character, so it's self-dual. And or just think about the abelian varieties. It's also clear it's self-dual. And so now you just apply local duality, the local Euler characteristic formula, and you get that the size of TP is the square of the size of the torsion points squared, but there are no torsion points over FP, because over FP n is not a square, and so there's an interesting Galois action, and it can't be trivial, and so this is one. Okay, so this is the local Euler characteristic formula that I'm using. Okay, so at least if n is not a square, you have all of these silent primes. We're going to use them. Okay, so now this was all kind of structural stuff about Selmer groups for these curves and Jacobians. Now let's actually start the proof all over again with our reduction assumption. So let's say we're given some quadratic field, okay? So the key thing is that this is not a square, so we're good. And so we're just given one. The first thing we'll do is we'll find some twist, some mu L twist of J Q to the L that has rank 0. This we can use the work of Mazur and Rubin, or really it's this theorem of U. So there exists R such that the Selmer group. So I start with the quadratic twisted guy, and I mu L twist by R. And U shows that for any given rank, you can find a twist, a mu L twist of that rank, in particular rank 0. And okay, so we use this. This uses the work of Mazur and Rubin, and it uses implicitly this notion of silent primes. I won't go into the idea of the proof is simply that you choose really carefully. If you're given, choose R randomly, maybe you have a big Selmer group. The idea is you just carefully choose a prime to twist a little bit more by to lower the Selmer group. And they show that you can do that. And U shows that you can do that in this context. And then you just keep lowering until you get 0. So we'll take this for granted, this result of U. So now we have one guy with rank 0. And so the goal will be to remove the Q to the L, right? Quadratic twist away and have something of positive rank. It's not clear how to do that. What we're going to do first, before attempting to do that, is we're going to find many, many, many other twists that also have rank 0 and with favorable properties. So we want to make a little bit of notation. So sigma S will be the bad primes. So P prime ideals dividing, what are the bad primes here? Well, any prime dividing L, any prime that's small, so dividing L factorial, and then the conductor, any prime dividing the conductor of the given guy that I'm starting with. So QL R squared. That should be enough. Okay, so this is my set of bad primes. Then I'm going to consider this much bigger set. Maybe I'll go over here. That's S. Let's consider sigma to be S, but then also all primes that are inert in K over F. So this is an infinite set now. And now I'm going to consider sigma units. So O cross F sigma. So this is the set of sigma units in F cross. Things with valuation supported on the primes, non-trivial valuations supported on the primes in sigma. Of course, sigma is an infinite set. So, usually you don't talk about units for an infinite set. That will only help us that this is a gigantic set. But yeah. Okay, so lemma. Suppose I have a sigma unit. Whoops. And suppose I further impose some congruence conditions, finitely many. Namely, locally at any prime P in S, my finite set, I suppose that the sigma unit is an nth power. So this is for all P in S. Then the phi Selmer group of, it's the same one as before, but now I'm going to further twist by T. And the claim is that this is still 0. So this is a flexibility. This is saying that there's a huge supply of T that I can further twist by, and I still have a trivial Selmer group. Yeah. Let's prove this. Sketch the proof. This is where the silent primes kick in. So proof. Yeah, so what's the point here? The point is I want to compare this Selmer group. I'm trying to show that this Selmer group is 0. I want to compare it with this one. They are mu L twists of each other. And so they're going to live in the same ambient space because the finite Galois module that I'm using to compute both Selmer groups is the same Galois module. So both cell phi JQL R squared and cell phi JQL R squared T squared live inside a common infinite dimensional FL ambient space, which I'll again call T. T is just H1F, J, QL, P. They both live inside there. And so what I'm going to do to prove that this we know has rank 0, to prove that this is rank 0, I'm just going to show that they're equal, that they're the same. And so we want to check, let's check that this is true globally, it's true locally for all primes P. So check that the WPs agree, that they're actually equal. And then it will follow that the Selmer groups are in fact equal inside T, and since one is 0, the other is 0. So we have to check it for all primes P. So there are kind of 3 cases. So one case is P is in this bad finite set, but I chose a congruence condition on T, and so if P is an S, then the curves are isomorphic. In particular, their Jacobians are isomorphic. And so, of course, the WPs are the same. They're naturally isomorphic and they're equal. Okay, so that case is handled by the congruence condition I imposed. There's also the case where P is an inert prime. So if P is inert, so if P inert, and maybe I should maybe, to be careful, I don't really need to do this actually. But just be careful, I'll also include ramified. I should have said ramified also. In the lemma about inert primes, it's true for ramified primes also. If P is inert or ramified, then yeah, maybe I should, just to be, I don't really need to do this, I don't think. Let's just throw in ramified. If P is inert or ramified in K over F, then as we saw by the lemma, TP is 0, so there's nothing to check. And then the other case is, so otherwise. So the point here is that we chose T to be a sigma unit. So every prime, yeah, actually I didn't need the ramified case. So every prime that has, a positive valuation in T is either in S or is inert. So these cover all cases, otherwise, except the case where you already have good reduction. Otherwise, both J's have good reduction. And in the good reduction case, it's well known that the WP is this canonical thing. It's the unramified subgroup of Galois cohomology in that case. It has good reduction and also it's prime to L. So in that case, WP is WN for both. And so they agree also. Okay, and so that shows that they agree. And since this one is 0, this one is also 0. Okay, so we have now this flexible supply of T that we can twist by and still get a rank 0 Selmer group. Okay, so now we're going to try to produce a point on the quadratic twists of those rank 0 Selmer groups. Okay, so a little bit of notation. If I have 2 elements of F, I'll write TAB for the class of, this is just to save writing this all the time, A to the L minus 1 over 2 times B. I think of it as a class, an L power class. Okay, so this is like a mu L twist that I can write down in terms of A and B. I will confuse the pair A and B and T, A and B. Like I just think of T as being indexed by A and B. Don't think too hard about whether there are multiple choices of A and B that will give you the same T, that kind of thing. Okay, and so right. So we're going to produce rational points by solving a unit equation. And I want to know that there are lots of solutions to a certain unit equation. So I consider the set X. This is going to be a set of twists, a set of classes of this form. So it's TAB. So A and B are in F. In fact, I'm going to consider only sigma units. So I'm looking at the set of all classes of this form coming from sigma units that satisfy the unit equation. A plus 2RB is equal to 1. So unit equation with constant 2R there. And then I need also this annoying but important congruence condition for all of the finitely many primes in S. So this is some subset of L power classes, and this is infinite. That's the proposition. So what I'm saying is that there are lots of solutions to the unit equation. Of course, my unit set, I'm allowing infinitely many primes, so it's of course not a contradiction to anything. And it should not be surprising that there are lots of solutions to this unit equation. On the other hand, actually proving that turned out to be a little bit annoying. We ended up having to invoke things that were much deeper than we expect to need to prove that there exist infinitely many solutions to this unit equation. And so I won't give the full proof, but here's the idea. You use a generalization of van der Korpit's result. This is how we did it. There might be other ways to prove it. There exist lots of solutions. So use a generalization of van der Korpit's result. What did van der Korpit prove? He proved that there are three-term arithmetic progressions in the primes. And more generally, he proved the existence of solutions to homogeneous equations in three primes. So the equation we want to solve is that the equation of this form, P1 plus 2 beta P2 equals P3 has infinitely many solutions. The solutions in the primes.
Some similar kind of thing appears in this Pagano and Koyman's approach, right?
So yeah, they use that there exists four-term arithmetic progressions.
Okay.
So they have to invoke like green tau.
But is it appearing for a related reason?
It's actually kind of funny, like it's almost opposite reasons as far as I can tell. Like they produce a rational point by just looking at a universal family where they have a rational point. So they don't have to do any work to produce the rational point, and then they use this four-term thing to analyze the Selmer group. We're doing the opposite. We've already analyzed the Selmer group. We're going to use this unit equation solution to produce the rational point. So whether somehow in a moral universe, I have no idea, but they're using a four-term arithmetic progression. We're using a three-term. So this is van der Korpit's results from the 1930s. I say generalization of because van der Korpit considered it only over the integers. We need it over the number, over a general number field. And nowadays, much more is known following the work of green tau. Say it again?
Prime means venerating a prime idea.
Yeah, and so this is maybe a good question. Like you might ask, what if there actually aren't any principal prime ideals that are inert in the quadratic extension, which happens sometimes. And so I'm hiding the details. You need to adjust the argument. But the main point here is that this is way stronger than what we need. We just want solutions to a unit equation. We don't care if they're prime or not. Like, by the way, like we're going to divide everything by P3 to get our solution, just to be clear. We don't actually care whether they're prime, so almost primes are fine. And so, yeah, so this issue about, primes not being principal, which isn't like it's an issue to think about, but it's not serious. You can handle it in the same way. So you use this to show that there exists these unit solutions. Okay. So the real question now is like, how are we going to use these unit solutions to the unit equation to produce rational points on twists? Before writing that down, I have just a technical lemma because I'm about to just write down a construction of a rational point on the twist, but we're going to need to know that it's not torsion. Like what if you write down a point and what if it's torsion, right? So here's a lemma. For n scalar, there are only finitely many mu-L twists, so L power classes, such that J and T squared F, the torsion points in Jn T squared F are not equal to the obvious torsion points. Namely, we know that there may be sometimes some phi torsion points. And what this lemma is saying is that there are only finitely many mu-L twists where there's interesting torsion. There's more, aside from some finitely many exceptions, there's no interesting torsion on these guys, on these twists. Okay, the lemma, I'll leave this as an exercise. This is a special case of a very general fact about the twists of any abelian variety. I won't prove this. This is not too hard. To formulate this statement, and for the general case is a little bit annoying, but you can generalize a statement to handle twists of any abelian variety. Okay. Yeah, and so now I'll just produce a point. So for all but finitely many TAB in X, and remember X was infinite. So that was the whole point of that producing as X is infinite. There may be finitely many exceptions where we don't understand torsion. But aside from those, the quadratic twist by K are given fields, which now removes the Q to the L, right? So now there's no longer a Q to L, or if you want to write it out in terms of A and B, it's this. This has positive. Okay, so that's the proposition. And the proof is I'm just going to use the relation. Where did my infinite set go? I'm going to use this relation to just write down a point. So I'm a little bit tired, so I'm just going to write it down and I'll let you check. But here's a point. On C R squared ABL minus 1 E squared. Okay, you check using the fact that it's satisfied the unit equation. This is a point on the code. And now the point is that A is not 0 because A is a unit. And so this point, which I think of in the Jacobian, it doesn't live in the phi torsion. Those are the points where A equals 0. So at least for all but finally many of these T, it has to be infinite order. So we have positive rank on the Jacobian. You might ask, where did this point come from? How do we think of this? And that maybe I'll write down. So this comes from the fact that these curves are covered by the Fermat curve. So this just comes from the map. Here, C tilde is the Fermat curve, AX to the L plus 2R. So it's a twisted Fermat curve, 2RX to the L. This one, this has a map to this. I can write it down. XY goes to AX over Y, A minus 1 over 2, Y minus L minus RB. Okay, some explicit thing. Now, the solution to the unit equation is the point 1, 1 on the Fermat curve. You push it down, you'll get some point, we write down the equations, and that's the point. Okay, and so now we're done because we keep this up actually. Oh, I just go to this board. Yeah, so now we're done because this point, usually, in other words, for all but finally many T, has infinite order. And it's in the Jacobian, J R squared T squared. T is TAB, of course. And so if A is J R squared T squared, then what we've shown is the rank of A over K. Well, this is, as I said, the rank of A over F plus the rank of the quadratic twist over F. And then by construction, this thing has positive rank. So this is positive. And we saw that the quadratic twist had trivial cell number, so its rank is 0. 0. So we got what we want. So this is the construction of the abelian variety that's desired. Okay, I'll stop there. Thanks.